Good morning everyone, and thank you for registering and joining us to this webinar on Polybrominated Diphenyl Ether, or PBDE. My name is Jean-Baptiste Bossa. I am Application and Product Specialist working in Europe for Horizon Technology, and I will be presenting this webinar. Is your laboratory ready for the new European standard PBDEs in whole water samples? This webinar will be about 30 minutes, followed by questions. It corresponds to a follow-up of the previous webinars we presented at the end of last year on polycyclic aromatic hydrocarbon within the frame of the new European standards published in 2015 by the European Committee for Standardization in order to support the implementation of the Water Framework Directive in Europe. The Water Framework Directive is a European Union directive adopted in 2000 which commits European Union members to achieve good qualitative and quantitative ecological and chemical status of all water bodies by setting up strategies and outlining the steps to be taken within an appropriate timetable. The framework comprises the development of a list of priority substances for action at the European level, prioritized on the basis of risk. This was achieved in 2001 following the decision 2455/2001 EC, in which a first list of priority substances became the Annex X of the Water Framework Directive. In 2008, the Directive on Environmental Quality Standards 2008-105 EC limits the concentration of 33 priority substances, thus amending the Water Framework Directive and updating the Annex X. Priority substances are chemical pollutants that pose a significant risk to the aquatic environment. There are currently 33 of these priority substances for which environmental quality standards were set at the European level. Polybrominated Diphenyl Ether, or PBDEs, are among these priority substances, and they are labeled number 5 on this list. Polybrominated Diphenyl Ether are also classified as priority hazardous substances, also defined as substances or group of substances that are toxic, persistent, and liable to bioaccumulation. In 2015, the European Committee for Standardization (CEN) completed the work that was requested by the European Commission regarding the publication of 3 new European standards to support the implementation of the Water Framework Directive. The objectives of these standards are to facilitate the monitoring of water quality by ensuring that national laboratories can measure the chemicals and ecological status of surface and groundwaters in a consistent and comparable way. These 3 standards specify methods for determining selected polycyclic aromatic hydrocarbon (PAH), organochlorine pesticide (OCP), and selected polybrominated diphenyl ether (PBDE) in whole water sample. EN 16691, EN 16693, and EN 16694 respectively. These 3 standards require us to perform solid phase extraction (SPE) with SPE-disks regarding the sample preparation and gas chromatography mass spectrometry (GCMS) for the analysis of these 3 groups of priority substances in whole water samples. CEN also published 1 new technical specifications regarding a method to determine tributyl tin (TBT) in whole water sample. This corresponds to the CEN TS 16692. The objective of this webinar is to present an analytical method based on the European standard EN 16694 that allows simultaneous extraction of a mixture of PBDEs from water sampling media. The chemical structures of PBDEs consist of diphenyl ether molecules containing 10 hydrogen atoms, which can be exchanged with bromine to varying degrees. This results in 209 possible congeners. The basic chemical structures can be seen in this slide, with the two halogenated aromatic rings joined by an ether group. This structure confers them specific chemical properties such as low water solubility, highly lipophilic, and therefore soluble in organic solvents. PBDEs are produced in three commercial formulations: technical PBDE, which is a mixture of lower brominated congeners containing 4 to 7 bromines, octo-BDE, and finally deca-BDE. The potential for bioaccumulation of PBDEs is directly linked to the size of the molecule. Lower brominated congeners, like commercial PBDE, are, for example, more bioaccumulative. Special attention is raised to PBDEs due to their persistence in the environment, bioaccumulation potential, and toxic properties. There is a growing concern about the toxicology of PBDEs because of their structural similarities to other polyhalogenated aromatic hydrocarbons, such as polychlorinated biphenyl or PCBs and dioxins. PBDE toxicity depends on the bromine content of the respective congeners. Toxicity decreases in the following order. Technical PBDE are more harmful than technical octa-BDEs, which are more harmful than technical deca-BDE. PBDEs in technical PBDE demonstrates highly affinity for lipids, therefore well absorbed and only slowly eliminated in biological systems such as animals and humans. They are expected to be carcinogenic, and exposure has been linked to tumor formation. PBDE mixtures are reported to have thyroid-disrupting properties and interfere with the hormone system involved in growth and sexual development. PBDEs are frequently used and applied in a variety of consumer and industrial products as flame retardants. In general, the use of PBDEs as flame retardants is in relation to their bromine content. Technical PBDE mixtures are mainly added to polyurethane foam, which are applied to car interiors, carpet, paddings, furniture, and pillows. Furthermore, small amounts of PBDE have been applied to electronic housings, textiles, and packaging. Landfill, wastewater treatment plants, and sediments are supposed major source of PBDEs contamination in the environment. However, transport, distribution, and direct emission source of PBDEs into terrestrial and aquatic ecosystem are not well understood. The European standard EN 16694 specifies a method for the determination of 6 selected polybrominated diphenyl ethers, or PBDE, representative for technical pentabrominated diphenyl ether, or PBDE, in whole water samples with mass concentration greater than or equal to 0.025 nanogram per liter for each individual congener. It is applicable to the analysis of PBDEs in surface water containing suspended particulate matter up to 500 mg per liter, as defined as whole water, but also applicable to drinking water and groundwater. The date of publication is March 2016. This is the front page of the European standard EN 16694 in its English version. The document is also available in French and German. As specified in the title, it is about water quality and more precisely the determination of 6 selected polybrominated diphenyl ether (PBDE) in whole water samples. These standards specify a method using solid phase extraction (SPE) with SPE-disks combined with gas chromatography mass spectrometry (GCMS). It is important to underline the fact that this method recommends the use of SPE-disks. I will further develop this important point in a few minutes. Here are depicted the chemical structures of the 6 PBDEs of primary interest, namely BDE container number 28, 47, 99, 100, 153, and 154. These containers constitute about 95% of the technical penta-BDE formulation, with BDE 47 and BDE 99 as the most abundant. It is important to remember that the term penta-BDE alone refers to isomers of penta-bromodiphenyl ether like BDE 99 or BDE 100. Technical penta-BDE refers to a mixture of brominated congeners containing 4 to 7 bromines, which has been identified as being of greatest concern with regard to potential exposure. Therefore, the method to determine PBDE should be accurate and sensitive enough to allow the detection of trace level concentrations in various water samples. This slide shows an extract of the European standard EN 16694, page 9, section 8, procedure and sample preparation. It is clearly written, do not filter the sample, hence ruling out liquid-liquid extraction techniques and cartridge-based solid phase extraction, by which it is mandatory to have clean samples. As mentioned earlier, PBDEs are highly soluble in organic solvents and poorly soluble in water. Any PBDEs adsorbed on particulates must be extracted along with the ones dissolved in the water sample. An external filtering of those particulates may run the risk to underestimate the actual amount of PBDEs in the water sample. SPE disks and cartridges differ mainly in their length-diameter ratio. This difference is beneficial for the disks because it enables higher flow rate and therefore a faster extraction. For example, 1 liter of a clean water sample can pass through a 47 mm diameter disk in approximately 15 minutes, but requires about 2 hours when using a cartridges. SPE disks are more efficient for larger sample volumes and for samples that contain substantial particulates such as wastewater or whole water. In contrast, cartridges may become rapidly clogged with particulates, resulting in a reduced flow rate and back pressure problems. To summarize, SPE disks are recommended for large volume samples, samples containing high amounts of particulates, and when faster flow rate up to 200 ml per minute is required during sampling. Now let's talk about particle size. The diagram on the left shows a typical cartridge with a packing materials ranging from 40 to 60 microns. And you can imagine a system like large rocks stored in a jar. If you flow the water sample too fast, you may run the risk to have channeling, meaning that the water sample can pass through without making contact with the particle, and you will not get the adsorption you are looking for. SPE disks, on the other hand, typically use 5 to 10 microns particles for the retention, therefore much smaller than SPE cartridges. Imagine this time the system like sand stored in a jar. If you flow now the same water sample, contact with particles occurs and you will get the adsorption you are looking for, and breakthrough is not possible anymore. This means also that we can use fast flow rates with SPE disks. If particulates are present in the water sample, they might compromise the flow through the SPE disk. In that specific case, the fast flow disk holder assembly can be used. This disk holder holds a regular 47 mm size SPE disk in the bottom, allowing also pre-filters to be placed on the top. This multi-layer of pre-filters protect the SPE disk from clogging, contain the particulates, and allow the water sample to flow through the SPE disk. If particulates are present in a water sample, adsorption of the analytes onto these particulates can result in low recoveries. Since the particulates are not discarded by external filtering, an eluting organic solvent rinses the particulates after the sample cycle and recovers the adsorbed analyte. For this work, solid phase extraction was performed on a SPE-disks 4790 automated extractor system loaded with the Atlantic brand C18 reverse phase SPE disks. The European standard EN 16694 proposes additional example of reversed phase solvent like hydrophilic lipophilic balance HLB or divinyl benzene DVB, also suitable for the extraction of PBDEs. The Atlantic C18 disks are certified for automation and they contain end-capped silica-based solvents with an octadecyl C18 bonded phase. The advantages of reversed phase bonded silica solvents are that they wet easily with both polar and non-polar solvents, and they are stable in pH ranging from 2 to 12. In addition, they are reasonably inexpensive compared to polymeric solvents. Conditioning and activation are important steps to guarantee reproducible recoveries. The Atlantic C18 disk may exhibit a considerable decrease in the retention of non-polar species if they go completely dry. Indeed, in its dry form, the C18 bonded phase is completely and randomly oriented, and the resulting non-polar surface is really small, hence decreasing the efficiency of the solid phase extraction process. The SPE-disks 4790 automated extractor system prevents this problem by continuously maintaining a proper wetting for more consistent performance. Regarding the HLB or DVB reversed phase solvent, they can go completely dry during conditioning and still be as effective without sacrificing the retention of compounds, making them easier to use in manual SPE disk system like the new SPE-Z manual prep manifold. Since we used an automated SPE-disks 4790, we used C18 disk without any reproducibility problem. The sample preparation summary is given in this slide. One should first collect and transfer the water samples into a glass bottle. Suspended particles, if any, are not removed prior to analysis. Remember that filtering out small particles such as sediment, clay, soil, or algae is not allowed. The exact volume of the water samples are calculated by weighing the glass bottle container before and after extraction. We then added 1.1 nanogram of the C13 label internal standard into samples. It is recommended to add the internal standard first to a water-miscible solvent, for example isopropanol, which is subsequently added to the water samples. We then spiked 2.8 nanogram of native PBDEs into the sample. The 47 mm disc holder was used because the water samples were not heavily particulate laden. If additional particulate was present and might compromise the flow through the disc, the larger diameter fast flow disc holder assembly would have been used. The method specified approximately 50 ml per minute loading for the sample. The vacuum should be adjusted with a low flow regulator in order to achieve such a flow rate. However, as it was demonstrated during our previous webinar on the extraction of polycyclic aromatic hydrocarbon, higher flow rates does not impact the performance of the method. Alternatively, on the new SPE-disks 5000 instrument, the vacuum, hence the flow rate, can be directly adjusted in the software. Finally, the extraction and elution of the PBDEs was started with the automated extractor system. The collected sample was dried and concentrated to a final volume of about 0.5 milliliter to 1 milliliter. The automated extraction method is explained in the next slides. The conditioning sequence is highlighted in green in this table. The first role of the conditioning reagent is to thoroughly remove any manufacturing impurities that might be present in the SPE packing material. Removing impurities ensures that the SPE disk will not contribute any background contamination. Here, the first conditioning solvent is hexane and removes any potential interferences from the SPE disk. The second role of the conditioning reagent is to wait or activate the bonded phase to ensure consistent interaction between the analyte and the sorbent functional group. Finally, the conditioning reagent makes the sorbent materials more compatible with the polar sample. Methanol is typically used as the conditioning or activating reagent for C18 packings. Following conditioning, it is often desirable to flush the conditioning solvent with an equilibration solvent. In other words, a solution similar to the sample load in terms of solvent strength and pH in order to maximize retention. Water is usually a good choice for reversed phase equilibration. On the left side is represented a schematic front view of the automated extractor system. During the conditioning cycle, the SPE disk holder is shown in green because this is where action occurs. The next step introduces and filters the water sample through the SPE disk. Once the disk has been conditioned, The extractor system automatically actuates the water inlet valve and delivers the water sample from the original sample bottle into the disk holder. It is during this filtration process that the PBDEs are absorbed and retained onto the solvent material in the SPE disk. During the sample cycle, the sample bottle, the water inlet valve, and the SPE disk holder are shown in green. During the drying step, residual water is removed from the SPE disk. In this process, the vacuum physically draws air from the laboratory through the disk as seen in green in the schematic view. At the completion of the air dry time, the vacuum automatically shuts off. It is important to remove as much water as possible from the solvent to avoid having too much water in the collected extract. This step sequence rinses both the original sample bottle and SPE disk using the solvent to extract the PBDEs. The extractor system automatically sprays solvent into the bottle as seen in green in the schematic view. The solvent is then allowed to flow into the disk holder and onto the SPE disk. This makes certain that any PBDE sticking to the inner glass bottle will be transported to the SPE disk and then eluted. In order to ensure high and consistent recoveries, the first rinse solvent used is a water-soluble reagent, such as methanol, in order to remove any residual water. The next rinse steps are performed the same way, but with a non-polar reagent like hexane. Please note that a variety of rinsing solvent may be used, but for large volume injection technique, a volatile solvent like hexane is more appropriate. This final step corresponds to the elution and collection of the target analyte into the collection vessel as displayed in green. This also completes the automated sample extraction process. All equipment or parts having contact with the eluate should be free from residues causing laboratory contamination. The dry disk or hydrophobic membranes can be used to remove any residual water from the sample extract. In some cases, a cleanup step with a multi-layer silica column might be necessary to remove interfering compounds. The eluate may have to be evaporated to bring the analyte into the concentration range detectable by the analytical method. This can be achieved with the XcelVap system, which is a water bath nitrogen blowdown evaporator capable of automating the evaporation of up to 54 individual test tubes. Alternatively, the DryVapor concentrator system is specifically designed to automate the drying and concentration of organic solvents by using a combination of sparge gas, vacuum, and heat to control the concentration process. Analysis of PBDEs gas phase samples was performed on a thermotrace GC2000 gas chromatograph connected to a programmed temperature vaporizer (PTV) inlet and coupled to a Polaris Q ion trap mass spectrometer. In order to achieve a sufficient chromatographic separation for all analytes, the oven temperature program was optimized. 2 microliters of a standard solution containing all native and mass labeled species was injected to the GC. Chromatographic separation of compounds was conducted on a Restec capillary column. Please note that other brands can be used as well. This description is given only as information for the users of these European standards. Here are the results. 4 water samples were spiked with 6 PBDE containers and subsequently analyzed. Quantification was based on peak areas. Native species concentration were calculated using the internal standard method and a calibration procedure. Mass label internal standard should be included to the analytical method in order to increase analytical precision. And injection standards can be used for the calculation of recoveries of internal standards. The recoveries are shown in this table. The PBDE spikes recovery are excellent for the full range of compounds as shown in the results. Finally, the consistency and reproducibility of the 4 samples is excellent as seen with the low relative standard deviation values. Now it's time to conclude this webinar. This work demonstrates the performance of automated solid phase extraction with solid phase extraction disks for the extraction of a PBDE mixture. Automated solid phase extraction using solid phase extraction disks complies with the method requirements of the European standard EN 16694 and provides excellent recovery between 70 and 120%. Automated solid phase extraction using solid phase extraction disks therefore meets the Water Framework Directive requirements. Further information on method and performance data can be provided later on. Before going to the questions, Horizon Technology would like to thank Licia Guzzella and Claudio Rossioli of the IRSA in Milan, Italy, for this help in producing this study. I would be really pleased now to answer any of your questions.